The first time we showed a demo at Dyson, we got asked that question: what does the model looks like inside, and how do you debug the models in case something goes wrong? Our response like, we don't know.
It's all about robot learning. Give us a brief introduction about learning robotics versus robot learning. There are some videos of humanoid robots getting out of control. What happened at that point in your understanding?
I saw the video and laughed and said at the same point. That one probably it was RL.
What was the previous conventional procedure of controlling a robot? Then why
Yeah.
RL came and what it helped it? Control system work on smoothness of the system. Does someone has to work specifically on the smoothness, or the model learns by itself? Very popular video once I saw that a person was giving a video feed to the RL model that he picks up a cup and place it somewhere else. Then a robot performs the same thing. So in your understanding, how this is happening? Robot learning, VLA, imitation learning, reinforcement learning. What are the differences between all of these? People who are getting right now into robotics and they have actual hardware directly start with reinforcement learning, or they should first go to control system and then RL? What should be the characteristics from robotic skills side that you are looking forward and find out that this is a good person that I would be happy to work with? Today we have Jafar Uruç with us on this podcast. He has been working as a senior robotics engineer in robotics learning. So hi Jafar, how are you?
Hey, thank you for having me. I'm doing well, thank you. How about you?
I'm good. Humanoid robots, robotic arms, all of these are getting very interesting, and especially the rise of robot learning. That's what we are going to explore in this podcast. Tell us about yourself. What's your robotics journey?
Yeah, so basically I started my journey with a startup in the US called Technic Robotics. The whole concept of the company is like doing consulting, but using open source. So we did like open source for a living, basically. We make money by doing open source development. I think after a few years, I moved my journey from like classical robotics to more of like robot learning, and I joined the Dyson Robot Learning Lab here in London. And after 2 years, Dyson shut down the whole robotics department. I moved on to doing my own thing for a few months. It didn't work out. So I joined like a humanoid company here in London. Then after a few months, I decided to move on to another robot learning company.
Okay, interesting. So it's all about robot learning. Give us a brief introduction about robot learning, learning robotics versus robot learning.
So it's a good question. I think robot learning is just applying this latest learning methods to solve robotic tasks. Before, like in like 4 or 5, 6 years ago, the way we solved any robot like problem that required robots is by using classical robotics. It's like the old way, pick and place. It's called see, think, act. A new method, you need this new method revolutionized it by just requiring data and some like cool robot like learning techniques, large models basically.
Large models. We'll come to the AI large models and their interference with robotics. So when things are evolving a lot in AI side, it's also started to affect robotics. So what's the difference when you look at AI for robotics and AI for different analytics, statistics? What's the difference between this AI models that we use in robotics now?
It's about the input and output. If you look at the LLMs or other, AI models, the input is like text, image, and output is text. Whereas for robotics, you need the interaction with the world. So the input probably is like text, like some instructions for the robot, bunch of sensor data, and the problem is like how you incorporate and fuse this data, then give an action, and all of them are all totally different spaces. Images like just like image space, like high width and 3 channels. And if you use like a depth view, it'd be 4 channels. And the output is literally the joint angles. Depend which action space you use, but people tend to joint angles for the robot. So the problem became because the robots you need to interact with the world. Interact with the world mean you have to move things around, touch things, and if you do something wrong, it's very catastrophic. So you don't want to have something wrong.
Yes, we don't want something wrong. But this happens. There are some videos of humanoid robots getting out of control. Just give a brief what happened at that point in your understanding.
I saw the video and laughed and said at the same point. That one probably it was RL, and because mainly people use RL for locomotion. Probably the model they didn't have a reward function for certain motions, because the way you train these models by shaping the reward. So you have probably like a term for aggressive motion, But yeah, I think they were trying, probably they trained on sim, so there's a sim to real gap. Probably something went wrong in the sim. They trusted the sim so much and deployed immediately on the actual robot.
We'll discuss that in detail because we want to understand robotics learning, policies, all of these jargons that come into robot learning. We will go in deep detail. Before that, what was the previous, or we can say older conventional procedure of controlling a robot? Then why
Yeah.
RL came and what it helped it?
Yeah, so the first one is actually teaching pendant. So if you buy a UR5, the ARM itself will have teaching pendant. In that method, what you do is you hardcode everything. You move the robot to some position, you save it, and move it somewhere else, you save it. And this one is very good if you have like full control of the environment. You have so many assumptions, like you know where the objects will be. So the arm will just like do a motion for like a few seconds, go somewhere else, wait for a few seconds. That one did not scale because, our world is more complex than just like fixed locations. Then we have the C thing act, which this require like you have the bunch of observations, which is like images basically, and like depth camera. Then you have classical or maybe modern computer vision methods, where like you do like object detection, then pose up estimation, and some like grasping. And after that step, you have the task planning, doing like planning for the whole task. They do like motion planning, and after you have like a solution, you pass it to control. You have so many systems in this approach, which means if you have like 0.9 success rate for each one, the overall success rate like drops because you just multiply the numbers. So it would go like 0.7 or 6 for the whole system because you have like so many subsystems. They have to succeed for the whole task to succeed. Now we move on to the newer method, like mainly is end to end. End to end is literally just you get the observations, images, and you output what should the robot do. And the middle is just like some complex representation by this models that actually we don't care about as long as it does the task for us.
Actually, we don't care about. Can you go deeper on this line?
Okay, that's a good question because I think the first time we showed a demo at Dyson using this robot learning methods, we got asked that question: what does the model looks like inside, and how do you debug the models in case something goes wrong? I don't like our response like we don't know. Like we don't know what's inside. It's just like a bunch of numbers and matrices that get multiplied. The way you maybe debug them, it's hard to debug. But the way you like see how they fail is just like run them in different environments and see what the model will output basically. In the imitation learning methods, if you're doing like some imitation learning or behavior cloning, if you go out of distribution, which is the data you collected to teach the robot, probably to do something reasonable because it's by definition the case. One thing people have been doing lately, which I saw like a guy had a GitHub repo for that, is visualizing the attention for the transformers and like to see like where the model pay attention most to. But again, like it's really hard to debug an issue. Neural networks are really powerful. They can like learn so many things. So sometimes you'll have a bug, but the model like still learns something. It's not very good, but it will up like something a little bit reasonable. So you have like to dig into code and see where exactly you did a mistake, probably multiplied, divided something.
Okay, that's interesting. We'll go into deeper detail of that with an example later. First of all, just want to clear up the control system approach and RL approach. In control system, we are applying different control methods. Let's take an example of robotic arm. So with a depth camera, we are looking at a table to perform pick and place. The next step is to segment the obstacles and segment the cube that we want to pick. That's computer vision. The next step is we have to pick it, right? So we give coordinates and the end effector moves towards solving the inverse kinematics, picks the cube and place it somewhere. Now, control system starts to act after the work of computer vision. But the point that I want to focus on is control system work on smoothness of the system and control outputs for the motors and the smoothness. So RL, does someone has to work specifically on the smoothness or the model learns by itself?
The model learns by itself. The frequency of the control or observation is kind of like a hyperparameter. I think there's a paper by Boston Dynamics did the work with the TRI, the large behavior models for the Atlas robot. In general, what people did is like you pass the output of the model kind of like directly to the low level controller. What they played with is reparameterizing the output of that model before you patch it to the controller. And they showed that it actually did not change the behavior. The reason why people were doing the other approach because they saw if you try the trajectory before you patch the low level controller, sometimes it like changes the behavior of the system for like different reasons. I think TRI in the article, Boston Dynamics pardon, in the article they said they found like you actually can speed up the inference by parameterizing the trajectory. For example, like optimal time trajectory parameterization, and you patch it to the low level controller. So yeah, in general, if you like if you look at the Act diffusion policy, I think they just patched the model will learn to generate the chunks, because a lot of these models they output chunks of actions, not just like one action at a time. So you generate like a long horizon actions, like 60 actions, for example, or 120, depending on the paper.
That's nice, meaning the smoothness, which is the core quality of control system, is
Yep.
easily being adopted into the network. That's nice. So moving forward, so control system is good. The last thing I think from control system and RL, the costs in control system, obviously it runs on embedded system. So what's the cost comparison between these two things? We understood one thing, that control system takes time much more than RL, because fine tuning in control system takes a lot of time and things. The costs comparison from your understanding between these two, with an example if possible.
I believe you mean reinforcement learning. So the reinforcement learning is like mainly used for locomotion these days, and I think it's the only way. Back in the day, people used to do like MPC, model predictive control, and like some complex trajectory optimization stuff to teach. But they found out like actually this locomotion, RL for locomotion is like really powerful, and they've been working really, really well. All this like cool videos we see lately, like backflip, they kind of like where possible. Boston Dynamics showed that they are possible, but I bet they did so much engineering to get that result, and like you need who knows how many PhDs to do that. Whereas like the reinforcement learning for locomotion, it just reward tuning. You literally like spend time trying to find the best reward function and the combination of like different things you care about. So what you need for reinforcement learning is like simulator, which is Isaac Sim. Isaac Lab, they have like something new built on top of Isaac on the physics called Isaac Lab. Another one is like Majoko Playground. It's like new as well. You use a simulator, you have the model, you run it for very long time. Not like you run so many environments in parallel on a GPU for like a few hours with like a domain randomization and a bunch of other stuff. And you will get like a nice policy that you can just deploy on the model, on the robot.
On
And
an
it will
actual
be,
robot.
what's that, sorry?
On an actual robot.
Yeah. So it's kind of more complex than that, because you need to also, there's other like tricks you have to do to be able to run it on the robot, but a lot of them are like zero shot. You just like train it, you like do some like tricks, and then you deploy it in the robot. And that cycle is like 8 hours. I have seen people who done it like in 1 hour. There's a company I met, I think it's in Zurich. They trained not on the fly, like trained for like an hour, and then you just deploy it in an actual robot. And you see the robot like, yeah, you just fine tune the reward.
How to teach a robot a behavior with RL.
Locomotion. The reason why
Locomotion.
locomotion, because it's only joint state. There's no visual input to the
Okay.
model. So it's,
Okay.
I think it's easier to have there's not much of a gap between sim and real. And there's like techniques people use. What they do is like learn like a latent space representation. So it won't be different between real and.
So let's move to the vision-based behavior learning systems, in which a very popular video once I saw that a person was giving a video feed to the system, to the RL model, that he picks up a cup and places it somewhere else. Then a robot performs the same thing. So in your understanding, how this is happening?
I think it's in context policy called Policy in Context by Vitalis, I guess. I did not read the paper carefully, so I don't know the exact details.
What's your idea that is that possible to teach a robot certain behavior through just a video?
Yeah, this is what we focus on actually in R2. So R2, the company I'm working with right now, the long-term goal is to have a demo condition. I don't know, like policies that's called it, like models, where you show it like a YouTube video and it will do what you show it. It will like understand what the task is, and the robot will do that. It's still like a research topic. I don't think like there's like one clear solution to that. Because the problem we have now is imitation learning methods is like they require so much data for generalization. And collecting data for robotics is one of the hardest thing. It's very costly, requires a lot of time, and the way we do it right now, I don't think is optimal. Because the way we record data these days is just by a person holding like an arm and moving it, the other arm will replicate what you do. And then you just record the joint state and images. I'm not sure if you've done it, but it's actually very exhausting if you do it for a long time. And it's not efficient for like humans, in my opinion. There's other methods, for example, the Oculus, the VR headset, but all of them like suffer from the same problem, in my opinion. It's really expensive to collect data. Unlike self-driving cars, right? You just drive a car, you collect data. For LLMs, it's just text. You just scrape the whole web to get those data.
So it's physical data is required, that requires physical effort in that scenario. And I just want to clear 3 words: robot learning, VLAs, and imitation learning. Let's add a 4th one, reinforcement learning. What are the differences between all of these learning?
So robot learning is the highest. It's just like a general term to use for any model that uses learning, like neural networks, basically. Imitation learning is supervised learning. So you need to show it the input and output, based on like input output data set. Reinforcement learning is learning from trial and error. If some people combine imitation learning and reinforcement learning, but yeah, robot learning is the high level for anything that uses neural networks. Imitation learning is supervised learning. Reinforcement learning is learning through trial and error.
Now let's try to extract things from your experience. Give us an example of imitation learning, or if it's possible, VLA in your experience for a project. Now, what I want you to explain in this process, how you did from the very scratch. I want information about tech stack, how you start the process, how you get the data, and how you test it on a robot.
Yeah. So I'll start from actually the simplest imitation learning model, which it's called CNN MLP. So basically, you use convolutional neural networks to get some visual representation, like embedding basically, and you have a model MLP, like a multi-layer perceptron, combine that data with the joint position data to output the actions. That model is kind of like very simple. You probably get it to work, but it definitely won't generalize. Then I would move to something more complex, which is ACT, the action chunking with transformers. That one showed like very promising results, and I think this was one of the first paper get a lot of people high. Now VLAs is vision language action models. It's a model that combines, like a vision embeddings with language embeddings to get some actions to send it to the robot. Simplest VLA is just having a text encoder, like language encoder and vision encoder, like ResNet, let's say, and you combine those with some MLP to get an output. Probably it won't be as powerful as the newest VLAs. That's really famous. Is Pi Zero. It's by Pi Zero. They open source their code and weights, and Pi 0.5. Going from how I will go from like 0 to actually deploying policy, the most important one is to have a data set representation. Like for us, I used PyTorch before. Now we use like a JAX. But for PyTorch, you just, implement a data set implementation, representation pattern, and then you have to create the data collection pipeline, which is what I default to in general is puppeteering, which like you have another robot, like it's called like a teacher follower setup, where you have like a teacher robot where like you move and the leader one would just follow you as you move. And you just save those data sets at certain frequency and save them that data set representing you had. And sometimes you do like post-processing, but a lot of people actually, I don't think they do it. They do like post-processing much.
What's the step in post-processing in this case?
One example would be to clean, when you do the teaching following setup, sometimes you do some stops. That might cause the model to learn to not do anything at certain stages. Sometimes you want to like avoid that stops because it would confuse the model. So you just discard the states where you don't move at all.
Okay.
And I found it, for example, personally, I found it like really help with my model. You don't see your model like doing somewhere like hovering.
Okay.
It will just like go directly do the task.
You mean you don't break into chunks, and wherever you stop you delete it, so it's like a continuous motion? That's what you were saying?
It's just post-processing. So you save the episode locally, and then you run a post-processing. Because sometimes people don't like to remove data they recorded. People love them. It's very expensive to recollect. So what you do is you just like run a post-processing on that episode, where if you see a step where you did not move at all, you just remove that one from your data set, from your episode that you save.
And it's totally application dependent that do you need this part?
I found it always necessary, but not everyone agree with me, so you can't fix that problem basically.
So I want to go a little deeper on the software development cycle system into this, I want software that you use and a data collection pipeline examples, that how do you collect data, and also the software's testing system and these kind of things that I want to understand for a specific example of, let's say, picking up an egg with a soft gripper with a 3DOF robot, Lee robot, let's say. Walk us through this process specifically from software development practice, your experience reinforcement side of robotics.
Yeah, because I would tell you, for example, what I did at Dyson. So Dyson, I led the whole hardware data collection stack.
Sure.
We had few hardware, not just like one robot. So we had to write a stack that would work for all of them. What we use at the time is Gymnasium. I'm not sure if you know Gymnasium. Gymnasium is just like a software abstraction for a reinforcement learning environment. Like you have the step, reset, and those shenanigans, like to get the observations. Use very simple roster control system to control the robot, because you don't want to spend your time supporting every robot in advance. We already have the support for each robot. We use the ROS subscription publisher abstraction to get the camera. But one thing you need to make sure you have is synchronization between different cameras. It already exists in ROS. It's a part of a message filter package in ROS where you could like synchronize different data streams. Then you pass that data stream. You have like two. Now after this, you have like two ways to do it. Gymnasium environment, you make sure like every time you step, which you expect like an action, you return those observations and use that environment for both data collection and for deployment when you run inference on the robot. That I use ROS, I would say, for any robotic related stuff. PyTorch, because it's easy to use. We like it for the modeling, dataset representation, and so on. We use Mijoko for simulation because we would like to first make sure the model works in simulation before we run it on actual robot. Another actually environment we use is called RL Bench, which has a lot of scripted demonstrations. It was written by the lead in our research lab. But it was like, I would say Mijoko and RL Bench for simulation. And robots, UR5, pandas.
What do you use for recording side and post-processing?
There's nothing interesting. Like post-processing is just like a function, like a Python function that will read all the data and the data set and make sure the difference between, like if the difference between two consecutive joint states is the same, it would just discard it.
More onto the software side. You work with Isaac Sim, Isaac Lab, and Mujuko. Then Gymnasium you are talking about. What differences do you feel in those things? ROS2, I understand ROS2 just for communication, but not with Gazebo. RL learning is not suitable for that. So give me a run through all of these software stacks and there's pros and cons for specifically robot learning. And also add the visualization tools as well. Do they help?
I actually don't like Isaac Sim because it requires a beast machine. I always default to Mijoko by default because it's very simple. And if you want to go complex and GPU, they support GPU. But if you want like something quick and hacky, like something like quick and iterate fast, I find Mijoko way, way better than Isaac Sim. Isaac Sim is GPU fast. You have to have a GPU. It will take a lot of resources from your machine. It's very powerful. Rendering, like nothing beats Isaac Sim's rendering. You have to say it. I used it like for consulting once or twice. We did collaboration actually with NVIDIA like 3 years ago, I would say. Support, move it with Isaac Sim. Me and Mark Rasmussen, we wrote an article about it. I think it's like 3 years ago. If you ask me personally, I only use Isaac Sim if the company I'm doing consulting for asks me to use it. Otherwise, I don't want to, use a lot of GPU for no reason. Bijoko is very lightweight, very powerful as well. Also, it's like written very nicely in my opinion. Some people find it like low level because it's written by, I feel like, heavy C people who like C. Like when you write in C, the naming is a bit awkward. It's like hard to read. But other than that, I find it really powerful, easy to use. Supports rendering is like a bad thing. You have to say it. The rendering is very slow and it's ugly actually. It's like it's a simulation, if that makes sense. There's another simulator called Sapien actually. I've been experimenting with lately, which is based on physics, the same physics engine that Isaac Sim uses, but it's way lighter. And you get the advantage of like rendering and the quick rendering. and good simulation.
Combining Isaac's Impros and combining
And
Majoko
Majoko.
Pose.
Yes, yes.
Okay, nice. So visualizations in robot learning, which tools, how do they help? With an example if possible.
Yeah, at Dyson I use Arvis because I like Arvis. It's kind of like written, someone wrote it like 10 years ago and it works, so we like it. It has a disadvantage because it's like GUI, so you have to always have a screen attached to your robot. Sometimes you don't want to do that. The thing that we're using actually lately is Rerun. I'm not sure if you use Rerun. It's just a really nice logging visualization tool. You can run it on web. So basically, you could run it on your machine, GPU machine, SSH into it, and see what's happening on your own machine by like just opening a link. It's really powerful, easy to use in my opinion.
That's nice. So let's just talk about the training part. You want to train a policy, and when I say policy, what do you mean by that? And also, if I want to train a policy and I have available models, creating from scratch is a good option. Using a model, what's the process in it if I want to fine tune certain thing and look into the output of the robot?
Yep. So policies, when I mean policies, just a model that output actions. It's kind of like synonym. If I say model or policy, it's kind of the same thing. I would say fine tuning or training from scratch. So some models, imitation learning models, for example, ACT, or diffusion policies, I would say you can train them from scratch on before VRAM machine. I would say you can train them on even less. The one I mentioned, like CNN MLP, is like very simple, small model. It's not powerful, so I wouldn't say pick it. I would start from ACT, which is like you can train on your own machine. I train on my own machine. It's like 8 GB from scratch. You don't need to do like fine tuning. Models, big models like the one released by NVIDIA Groot, I believe it's called, and Pi 0 or Pi 0.5. Those are like beasts. I think they train them on like 8 A100, if I'm not mistaken. Fine tuning is just like also expensive. It's not cheap for those. But yeah, those models, my experience, they did not generalize. When I deployed them on like new robot, they wouldn't generalize. They would like do like random stuff. Some things that doesn't make sense. So what you do is you just go collect data. You have to make sure it's the same representation that Pi 0 wants you to use. And then you just, they provide the script actually to do some fine tuning. So you just run that script with your new data and wait for like 4 days maybe or a week. Pi 0, every fine tuning cycle takes a few days on 4 A100s. It's not cheap. So they provide LoRa fine tuning, which like some require like less GPU, but it won't be as powerful as fine tuning.
A lot of learning, robotic learning. Let's move towards the career path of it. People who are getting right now into robotics and they have actual hardware, or let's say robotic arms, not humanoid robot, they are costly. So what should they start with? In an example that if you're saying they should not go with the conventional control system side and they would directly start with reinforcement learning, or they should first go to control system and then RL?
So it depends. My recommendation is like start from the basic robotic stuff, which is like very simple rotation matrices, homogeneous transformation, maybe reach some like trajectory, like the dynamic, like some like dynamics, high level dynamics and kinematics. And I would say just jump to the robot learning stuff. Why would you like study, for example, MPC if you're interested in like manipulation? I understand like maybe it has, but if you're like just coming into the field, you need to motivate yourself. And the best way to motivate yourself is by having some like nice demos that you can run yourself. So I would say there's a famous book, it's Introduction to Robotics, I believe it's called, Robot Manipulation. I will share the book if people are interested, but it's a very well-known book. But basically, I would say start like at the first few chapters, I think till the fourth chapter. So basically, kinematics, Jacobian, maybe dig a little bit into like Newton method, like the Newton forward method to calculate the dynamic or the backward one. Then I would say just like there's very famous library called LeRobot, which they've been like trying to get people like hobbyists into robot learning, and it worked really well. So I would say use that one to get some really nice, cool demos that will motivate you to even like explore the field a little more.
I want some examples of what kind of colleague that you would look forward to. And I want to understand in your specific role that what should be the characteristics from robotic skills side that you are looking forward and find out that this is a good person that I would be happy to work with.
Okay, that's a very good question because this AI time where we have like vibe coding and everything, one of the most important skill is moving fast, I would say. And unfortunately, like I think Andrei Karpathy said that. He said English language is the most important like programming language now, and it's reality. I think if someone is like open to new ideas and exploration, that's the best skills they can have now. The execution with vibe coding like became a bit easier. It's not the best way to execute stuff, but if you want to iterate fast on ideas, it's definitely the best way to do it. Being
Yes.
open is, back in the day, Googling was a really good skill you look into for like when you hire new engineers, right? I think now it's like prompt engineering. If someone knows how to prompt this like models, they can do a lot of things without supervision. Understand the basics 100% is like crucial. I would say at these rotation matrices, homogeneous transformation, Jacobian, those things are crucial that you actually use in robot learning. When you do like some robot learning stuff, you would use those stuff. Not the dynamics. You won't probably calculate, like do any inverse dynamic stuff, but Jacobian, some rotation matrices here and there, those are like, you would use them.
Interesting. So, as a robotics engineer, have been in the field for a long time. What do you see your actual work to be as a software developer or a researcher? What's it look like
When I worked as a developer and now like more of a researcher or in general?
nowadays? And if you can give a comparison between your previous software development to researcher, what's the differences?
Okay, so Picnic was pure software engineering company. Dyson was pure research lab. I would say difference is like in software engineering, you care about quality, maintainability of your software. So when you write software, you need to make sure it's maintainable and it works reliably. Researching, I would say you want to like move the field a little bit forward and you want to prove a point, like prove something that's feasible. So I would say maintainability is not something you care about. And actually, a lot of this papers like kind of like self-contained. And if people want to use them, if you look at the GitHub, you'll see like the code, there's a bunch of commented out the code and random like hacks here and there. They want to get something running and prove the main point. The pace is different. In research, you chase publish like conferences. So your deadline is like the next conference, probably. Software engineering is like for us it was more consulting, so it's like our client. Like software engineering, you care about like reliability. You want your system to work long time, like reliably. Whereas in research, if you get it to work, you just like you publish the numbers you have.
Okay, nice. Let's say for now, as a researcher, and in the scenario that if things go out of control, software is not good quality or tested, it can cause damages. So, as a researcher in this field of practical testing AI models on the robots, robot learning models, so testing from software engineering side, testing practices are now important. Is that the case or not?
It is important. So the company I work with now, I'm not researchers, I'm more focused on the hardware and robotics stack than actually writing models or helping with like deploying models or like data collection. And the people, they all like ex-Google. So it's kind of like the quality is really, really good here and we care about that. What I mean is like when you work on research, you care about like moving the field forward or like having a new novel method. For software engineering, you don't care about that. You care about like abstraction and how to make it usable by other people easily.
Next thing, in robotics, most of the people are working physically because robots are physical, and there are some people who want robotics remote jobs. So what do you think? Is it practical for specifically robot learning, as we are looking at it as a going to become sort of a standard and not using control systems? So remote jobs are possible?
That's a good question. My picnic job was mainly remote because at the time we had COVID, if you remember. Like during that time, it was COVID and it was feasible because simulation, the classical robotics, you could kind of replicate everything in real in simulation as well. So for classical stuff, I would say yes, it's more feasible, more like robot learning. If you're doing the modeling stuff, so you just write like models, yes, it's feasible, but probably the company require you to be in office a few days a week. You need to run an actual robot, otherwise it's meaningless. But in general, I would say yes. It's harder to find remote jobs than for classical. Reason is like you have data collection, you need to be next to the robot. Inference, you need someone to be next to the robot as well. Plus, you cannot rely too much into simulation to make a conclusion on the actual robot. Because so for manipulation, because a lot of input is like images, the real gap is actually massive, and you just cannot rely on sim data and deploy it on actual robot. There are people who did like they got some results, but in general, the gap is big and it's not possible at the moment with any of the models that exist, in my opinion.
So no remote jobs.
Unfortunately, I would say if you're doing robot learning, you'll struggle to find a remote job. I might be wrong, but if you're doing modeling, probably they will let you do a few days here and there. I'll give you an example, right? My current company, R2 Reimagine Robotics, they give me a bunch of robots, so I have in my room a lot of robots.
Okay.
So I can't do things home, but
Mm.
I need to be in office 3-4 days a week to make sure the robots in the office, like when you write software, they work. Like you need to improve your data collection process, or like sometimes deploy models, run them, make sure they're working, and so on.
Okay. So what's the future we are looking at? There is NVIDIA, Omniverse, Isaac Sim, Isaac Lab, whole system they are producing. They are producing open world models, growth models, and a lot of things they are providing. So what's the future we are looking at? Just sort of text to behavior things, and is that what we are looking at?
There's different companies and they work on different things. I would say physical intelligence, they work on foundation model. So they work on like foundation robotics model, similar to LLMs. LLMs like a big model that you could have wrap it in some way or like fine tune it for different applications. I think that's what physical intelligence are trying to do. There's Dyna. Dyna is another company in the US. They had a raise round recently. I think a lot of money. I forgot how much, 600 mil maybe. They doing more application focused. So their approach, I believe, is like solve one application at a time, one problem at a time. And I think the one they showed is like generalization. They run it, I think, at Call Conference. They like literally zero shot. It like was able to do it on the stage. They're doing more of I think reinforcement learning on top of VLAs. If I'm not mistaken, there's Figure AI. They do an in-house model. They built like Helix, which is like system 1, system 2 kind of approach. But in general, I would say we have people also work on like some open source where like it's accessible to everyone.
So a good future that we are looking at.
Oh yeah,
Easy.
definitely good future. I doubt like none of the models we have now generalize, in my opinion. Just from my experience, like generalization is still like a question. But if you fine tune, you get really good results. They're betting on data, right? So physical intelligence, I believe they bet on like having a lot of data, and you have a really big model, and it will generalize somehow.
Nice. And they are trying to extract the data from videos.
Oh no, I think it's just the teacher follower kind of style.
We'll sort of have another podcast after 6 months to understand what the next things are coming. So I think this direction is progressing very fast. Physical AI, embodied AI. So we need quick thoughts from the researchers in this direction. And thank you, Jafar, for your time and discussing this important topic, because a lot of people want to understand this. And personally, I started into this side as well. And it's quite interesting to look at things happening without control system tuning and still good behaviors of the robot. Thank you again for joining us.
Thank you for having me, man. Thank you. Cheers.